All right, so it's recording. So, folks, we were talking about already lost my. All right. So we were talking about. I don't know what is. Wait. Let's see if I can do this spotlight video on this. That might work. See if I can see. So we're talking about dynamics, right? We got to a point, basically, we said, well, dynamics includes kinematics and kinetics. We said, well, we've been actually talking about kinematics without even referring to it by its name, but pretty much kinematics includes position, velocity, and acceleration, what we were talking about before. And then we started looking into kinetics, and we said kinetics adds what causes the motion in an object or in a rigid body or in a particle as a kind of idealization of an object. So when we take into account kinetics, it means we are also looking into what is causing the motion in an object. So dynamics in general, it means we are studying the motion of a particle, and we not only look into the motion itself, like position, velocity, and acceleration, kinematics of the motion, but we also look into what is causing that motion, right? What kind of forces or torques applied to this object or this rigid body or this, again, particle as an idealization causes these motions. Now, we reviewed Newton's laws, and we said, well, in statics, we were mainly focused on Newton's first law and the third law. In dynamics, we are more interested in second law and third law, because that's where things start moving, if you want to think about it that way. And we are out of that equilibrium, static equilibrium zone. Now things are accelerating or decelerating, depending on how the motion is happening. So we're looking into Newton's second law, because that's where we get the information about what happens if the net force, or all the summation of or vector sum, or vector sum, as a good phrase, vector sum or net force applied to an object is non-zero. What happens? Then we said, well, this law tells us that the object starts accelerating, and as a result, the Newton's first law should be expanded, which becomes Newton's second law, meaning that the summation of forces now is equal to ma, m being the mass, a being the acceleration. So F is a vector, a is a vector. So the higher the force, the higher the acceleration, or the higher the acceleration, the higher the force. And acceleration and force, both vectors, so you can get a sense of directionality there. They should be along when you apply your force. At least the acceleration caused by that specific force is along that force. And the third law is still there. For every action, there is an equal and opposite reaction, because that we actually need to be able to study the motion and draw the free body diagrams. Now we said, well, first, so the general idea is that we look at the free body diagram, which we had from before from statics. Now what we add to it is a kinetic diagram. We said in kinetic diagram, well, kinetic diagram is nothing but a diagram representing all the components of acceleration. We studied the acceleration when we were looking at kinematics, or position, velocity, acceleration. And we study acceleration in different coordinate systems. We study acceleration in Cartesian coordinates, in normal tangent or tangent normal coordinate system, and in polar coordinate system. Now the same story here. Depending on what your coordinate system is, you're going to have some components of acceleration and some components of force in that system. All you need to do is that draw the free body diagram, find the components of your force in that coordinate system, make it equal to kinetic diagram, which basically is the components of your acceleration multiplied by the mass of your object. Right? That's pretty much what you need to do. So you use what you learned in statics plus what we learned in the first part of the semester. We spent quite some time on that for 4 weeks, and just put them together. And as long as you know how to do vector operation, you're good to go. Right? I give you an example, a simple one. No object there, just some force vector. Then we went over another example with the body, and I talked about how to draw the free body diagram. Well, you already know that, just reviewed the free body diagram. And I told you there are 5 forces. Keep in mind when you're drawing the free body diagram, when you're isolating a part, think about these 5 forces. Spring, we'll start with, let's go with weight, contact, smooth contact or normal force, friction, force of a spring, force because of a spring, and force because of a rope or a chain or thread or whatever that is that can only handle tension. Right? These are the forces you again studied in statics. And make it equal to kinetic diagram. And kinetic diagram again is just the acceleration, wherever the direction of your acceleration would be. And from there, you get a set of equations in Cartesian coordinate system. Typically, you get one in X, one in Y direction. And if it's in 3-dimensional space, you get in Z direction. The good news is almost never in this course, we're going to talk about 3-dimensional dynamics. So I guess that's an EA for you, as opposed to statics that we actually talked about vectors in 3-dimensional space, and we talked about rigid bodies a little bit, and how to calculate moments in 3-dimensional space. Here, we're just going to stick to 2-dimensional space, and everything we cover, almost everything we cover is in 2-dimensional space. So that's one thing to be one less thing to be worried about, I guess. Now we got to this example. I just gave you the problem example, the statement of the problem or problem statement, and we didn't really get a chance to talk about this. So let's start from here. Go over this example, and I have multiple examples, couple more. We'll see how many we can cover. And then in the next class, we'll talk about same story in tangent normal coordinate system. All right, so this example, you should have it from before. We had 2 weights. One is on the surface, horizontal surface, in contact with the surface. There is a friction between that weight, 5 kilogram weight, and the surface. And the coefficient of kinetic friction for that is 0.18. And that weight is connected to another weight, which is hanging. It has a mass of 10 kilograms, and the connection is through a rope passing through a pulley. Right? And we said, remember the same assumptions we made in statics about ropes and chains and threads. We said they do not stretch. They're always under tension. If there is a rope under compression, it means we can just ignore that rope or chain. And we said the force is the same throughout the rope. These are the main assumptions that we make about ropes, chains, and cables, generally in statics, dynamics, in most of courses in engineering mechanics, in mechanical engineering. So let's start with what we know, right? So the first part is asking, what is the tension in the cable, right? Again, the tension is the same. It's a cable, so tension is the same throughout the cable. Now, to get the tension, obviously, the only tools we have, and we know what we're doing in this section, hopefully at this by this point, that you find the object, you find the part that you want to draw the free body diagram for, isolate that, come up with the free body diagram with all the forces. Now, in dynamics, we add kinetic diagram to it, and then write the equations and see how can we take it from there, and what unknowns you have, how many equations you have, how can you fix it, or how can you find the unknowns. All right. So I have some technical problem here. And I don't know how to solve it, so I'm working on it. Okay. Let's do this. For some reason this just doesn't like me. I can just live with that. Can you guys see the whole screen? Share screen, or it's blocked part of it?
I think we can see all of it.
You can see all of it?
Yeah, all the problem statements.
All right, all right. Let me see if I can get rid of this. There we go. I can't move it. All right, I'll just look at that. And now I lost one. All right, now they're going to start. All right, so where do we start? Remember, I told you, well, I don't know if I told you in this course, but generally speaking, when you want to draw the free body diagram, you have two options. You either go for the part of the system that you have the most information about, or you go for the part of the system that you are asked to find a specific unknown about it. Right? Typically, I would, if I want to prioritize that, like if I want to give an order, I would say, let's start at looking the part of the problem that you know the most information about. So in this case, well, 5 kilogram weight, we have the mass, we have the coefficient of kinetic friction it has with the surface that is moving on it. So logically, or better to say, most probably is the best place to start. Look, best place to look into and draw the free body diagram for. So that's where I'm going to start. I'll isolate this, right? I want to draw the free body diagram. So I'm going to isolate this. And I'll draw the free body diagram here. Let's say I have, let's do it here. I have free body diagram right there. Remember, now we have an added component. So I'm going to draw two because I want to draw the kinetic diagram. Right. Now this would be, let's call this M1 because it's easier if you have names, and call this M2. And I'm going to say M1 here, M1 there, equal. So free body diagram on the left, kinetic diagram on the right. So this free body diagram, this is kinetic. It's an ugly way of writing it, but diagram, all right? Okay, looking at free body diagram, what do we have there? What forces do we have there out of those five?
The tension from the wire.
We have a tension wire and it's to the right. We have the friction to the left. Yes, so so that's going to be the tension. That's going to be the friction. And let me also put the direction. This is our tension. This is the friction. I'll show it with FK since the friction and it's moving. What else? Obvious ones. We have the weight, exactly, downward, and out of those fronts. Sorry, what?
The normal force of the object.
Exactly, we have the normal force. Thank you. So down, this is upward. Let me just put the directions. So that would be the weight, M1G. Maybe I can write it better. M1, the M1G, and this would be normal force N. We only have one N, so I'll just go with N instead of M1. On the kinetic diagram, what is the direction of the motion? You know, if we have, let's say, I take my coordinate system X and Y. What components of acceleration do I have there in Cartesian coordinate?
One acceleration to the right.
Yeah, exactly. There's only one acceleration to the right. Thank you. So make it this way. And that's pretty much it. And the component would be those kinetic diagrams, so you have to multiply it with the mass. Let's call this MA, let's call this AX. All right. Once you have this, the rest is just writing the equations. And so the summation of forces, should I write it in front or let me write it here. Summation of forces is equal to MA. Right? You have to decide about the positive direction. Rule of thumb, if you want to get the right answer, and you'll see it in vibrations, that is actually a must. the direction of the motion is the direction that you typically should take it as positive. So keep that in mind. I mean, if there is no motion, like in this case, in y direction, doesn't matter. But in x direction, since the motion is to the right, we take that as positive. So I usually put it here to remember that this is my positive direction. Well, let's just put it on, this is the general form. Let's just put it on the x. So summation of forces in x direction is equal to m1 ax, and summation of forces in y direction is equal to m1 ay. And I'll take this as positive. For y direction, since there is no motion, it doesn't really make a difference which direction you take as positive. If you had a motion, probably, not probably, that's what I suggest. Take the direction of the motion as positive so things don't get confused. I'm giving you a bunch of rules that you just follow and they always work. So less doubts with what you're doing. So from the first one, right, I'll just keep both of them and continue using both together, or putting the components for both together at the same time. For the first one, summation of forces in x direction. So we have t in the positive direction, right, minus, then we have fk in negative direction, right? Get better fk, we can write fk is equal to, there's nothing on the three-body diagram on the left side. We come to the right side. The right side, we have m1 ax. m1 ax. Second equation, fy, summation of forces in y direction, or n, minus m1g is equal to, there is no component for acceleration, or there is no component on kinetic diagram, so that would be 0. So from there, the second one gives you n is equal to m1g. Fk, you already know, friction is equal to mu k. Maybe I should use a different color. Friction is equal to mu kn, right? That we already know the definition of friction force. So that if I plug in n from the second equation in the first equation, and let's do it this way. Then from both of them, so later on when you look at this, hopefully it makes more sense. From both of them, you will get t minus mu k m1g is equal to m1 ax, right? This is what we get from these two equations, basically, just putting them together. Now, looking at this, I know the value for mk, I know the value for m1. M1 is 5 kilograms, mk is 0.18, g is acceleration due to gravity, m1 I know. I don't know what ax is, and I don't know what t is. So now the problem is I have one equation, two unknowns, right? Not a fun place to be. This is one equation and two unknowns, right? And two unknowns. So stuck, right? I need more equations because I can't do anything with my unknowns. I don't know t and I don't know acceleration. So how do I get the and second equation? Hopefully half of you are already there and you know where I'm going with this. I look at the second mass, this whole system, right? The system is moving, and I have the whole system to study. So the second thing I have in hand, the only thing that I can basically go to as a last resort, hoping that it gives me another equation that I can deal with this one equation and two unknowns. Hopefully I can find one unknown from there, is the second mass there, right? So that's what I'll do. I go to this one and I isolate this now. And I draw the free-body diagram for that. So with the danger of squeezing things together, I'll just put it here. This as being the mass for, and this is equal to right there. So the left one being free body diagram, right one being kinetic diagram. No, now forces. Let me just write, this is M2 and this is also M2. So forces, what forces do I have on M2? Looking at free body diagram, out of those 5. Tension upwards, weight downwards. Exactly, Rich. Thank you. So tension upward, weight downward. I got into the limit of my board here. This, I'll call it T. Remember, tension is the same throughout a cable or chain or force, or a thread or wire. That was the main assumption we made when we introduced those 5 forces. We were talking about these 5 forces in statics. And this is the mass. This is the weight, M2G. How about the right side? If the mass on the top is sliding to the right, what would be the direction, or better to say, what would be the component? Exactly, downward. M2AY downward. Exactly. Thank you. So we put it this right there because it's moving downward. So that would be M2, and we call this AY. And that's pretty much it. It's not swinging. Hopefully, if it does, then the things are going to be a whole lot more complicated. So from there, summation of forces again is equal to MA. I'm not going to write the one in the X direction because nothing is going on in X direction on either diagram. So just let's ignore that. In Y direction, so I'll just write it this way. Fy is MAY. As I said, I take the direction of the motion as positive when there is motion. So now we have a motion downward. So what I'm going to do is that I take downward as positive. From there, you'll get M2G minus T is equal to M2AY. And from there, let's just write it as T. Maybe it's easier to look at it. T is equal to M2G minus M2AY. So I got another equation. Now, I know what M2 is. Well, I know what G is. M2, I know what it is. Do I know AY? Well, I don't know T either, but T is the same unknown. How about AY? Do I have any information about AY? Or it's going to be another unknown? Because if it's another unknown, I'm going to get, again, one equation with 2 unknowns. So I'm going to end up having 2 equations, 3 unknowns, right? If this is my first equation, we don't get lost there. This is equation 1 right now, and this is equation 2. Now, what I want to have is that I want to have 2 equations, 2 unknowns, so I can solve it mathematically, right? Now, T is 1 unknown, but now I have AX and AY, right? How do I deal with that?
I might be
Roughly
wrong,
equal to each
but
other.
Okay, so I heard a couple of answers, but I couldn't really follow either of them. Can someone just, one of you guys go?
Sam, you go first.
okay. I was gonna say might be wrong, but wouldn't the acceleration in the Y direction just be 9.81?
All right, one opinion. Anyone else?
I was going to say, because they're attached to each other, the accelerations are constrained by one another, so they have to be equal.
Exactly. Right. So that's where basically I was trying to go. That now, if it was a free fall, somewhere you were right. You would be right. If it was a free fall, then the acceleration would have been just G. But now it's constrained and it's going down. not by gravity, but because of its connection to the other mass. Right? Now, gravity is pulling it down because of the effect of weight we put on free body diagram. Right? So that acceleration is there on free body diagram. It's doing its job. It's pulling it down as weight. But remember, we have two things. We have what is causing the motion and what the motion is. All right, two sides of the equation: kinematics, kinetics. Now, kinetics, like the left side, T, M2G. These are the forces that are causing the motion. Kinetics. Hopefully, I said it correctly. Kinematics, when I come to the right side, tells me, so what happens because of those forces? Then that's something that we need to figure out. What is the acceleration? How fast this goes because of the force T, tension, and the weight downward. That's something we actually have to find out. Now, but because these two are connected, you can imagine that if this one goes to the right and this one goes downward, obviously these two are connected objects. So they move with the same velocity, they move with the same acceleration. Because one cannot move without the other one, as long as the motion is in this way. Can be true the other way as long as M1 is causing the motion. But let's not make things complicated for now. So the acceleration is the same, right? AX and AY, they are the same. Let me just put those in notes. So both masses are connected, or better to say masses are connected. I don't know where the both come from. Masses are connected by a rope. So they have the same acceleration. So AX is equal to AY. Right? Once we establish that, then we're good. Then we have two equations, two unknowns, right? From the first one, I'll get, let me write everything as function of T for both of them, so it's easier to follow. The first one, we get T equals to M1 AX plus mu K M1 G. M1 AX plus mu K M1 G. And for the second one, we get M2G minus M2, I'll just go with MX. M2G minus M2AX. So now it's good. Now the only unknown here is T. Everything else, we have two equations, two unknowns, sorry. So we have two equations, two unknowns. Right. Mathematically, we should be able to solve this. You can just make both sides equal. Let's say, since both have T, let's say make the right side equal. You'll get M1 AX plus mu K M1G gives you is equal to M2G minus M2AX. Then we can just move things around. If I simplify that, M2 and M can factor out. Did I make a mistake somewhere? 2, no. So if I move that one this side, that would be M1 plus M2 AX is equal to M2G minus mu K M1G. I just want to write and find acceleration, or the part A is to find the acceleration. So A, or AX, I want to call it, you can just call it A at this point because it's just the acceleration. Let's just make our life easier. I'll say AX is equal to AY is equal to A. All right, that's pretty much it. So let's just convert this, make this A. You don't need to keep referring to it as AX. This also, I can write a better A there. and with the correct color, hopefully. So acceleration becomes whatever we have on the right divided by whatever we have on the left, m2g minus mu k m1g divided by m1 plus m2. All right, you plug in the values. M1 was 5, I think. M2 was 10. Then G, you already know, 9.81, 9.81. M1, 5, M2, 10. Let me double check. M1, 5, M2, 10. And you also know mu K is 0.18, right? So plug in all the values, you'll get, let's just put it under A, right? This is the answer to part A, acceleration. So acceleration becomes, I gotta check what the final number is. The acceleration becomes 5.9514 meter per second squared. So that becomes your acceleration. Part A. Actually, part A was not asking for acceleration. Now I'm thinking. Tension. All right. So you don't really need to do that. Once you know the acceleration, it's two equations, two unknowns, so you can find you go back to your set of equations. You know A, plug in there, you can actually find tension. So from star, I'm gonna put star here. Either of these equations should give you value for tension, right? That'll be, plug into any of those, you'll get 38.586 newtons. Okay, now we can say this is what part A was asking. Now part B, always go to the wrong page. How fast the weights are moving 1 second after they are released. So how do we do that one? Now that we know acceleration, we know tension, we want to know what is the velocity after 1 second. Right? Just goes back to kinematics again. Now you have acceleration, and acceleration is a constant number, so we can basically just find the velocity, right? Hopefully you follow. V would be AT plus V naught. I don't know if the problem somewhere mentioned, hopefully anything about the is released from rest. So there you go, is released from rest, meaning that your V naught is 0, the initial velocity. So that becomes 0. This becomes 5.9514 after 1 second. So pretty much is 5.9514. Don't know why they carry that many digits, meter per second. This becomes your velocity after 1 second. Question on this one, right? All right, I went slow, so hopefully everybody follow. All right, next example. So if there is no question on this, I can look at I can bring up the next example. So hoping we can go a little faster, we'll see. I try to go faster in the next example, and I'm hoping that you're going to stop me if. Example. Now in this one, we have a truck that is, let me draw it, or do my best trying to draw it. This is my best way of drawing this, whatever. should be connected there. And then we have it there. Let's say there's a tire there, another tire there, and gosh, harder than I thought. So we put it here, and then I have this right there, and hopefully we get some tires there. It's not. There we go. Not bad. Then you have a box, or that box went totally wrong. So there we go. Let's try to do that. And then there goes the box sitting there with a mass of m, and the friction between that and the bed of this truck is mu k is 0.64, coefficient of friction, kinetic friction. And this is going in this direction. This is the direction for the acceleration. And you're also given this angle 30 degrees. So the problem statement says there's a box of mass m. I'll just put the box is resting on the bed of a dump truck. We know the coefficient, we know mu k. What else? Let me see. Now, in order to make the box slide, got lost in my own problem statement. Slide when the bed is in the position shown, is in the position shown, the truck must accelerate to the right, which I basically put it on the figure. Now, find the smallest acceleration for which I don't know where did that come from, for which the box will begin to slide. Hopefully it makes sense what the problem statement is. All right, so we know what we're doing, right? Draw a free body diagram, find the forces, look at the equations, and see how things go. That's the best way I can describe it. Very not straightforward, but there is really no other way to do this or to do these problems. Find the part that or the part of the system that you want to study, or you're interested, or you're asked about it, or you're given the most information about it. Either of these. Isolate that, draw the free body diagram, draw the kinetic diagram, make it equal. Look at the equations. see if you have enough equations for your unknowns, and you can find what you're asked. So in this case, I'm going to isolate the box and draw its free body diagram and kinetic diagram. So here I'm going to put two of these together. One for free body diagram. I don't know why I magnified the size of the box, but there we go. And here is the one for kinetic diagram. So that would be my free body diagram. That would be my kinetic diagram. All right. Forces on free body diagram. What do we have, folks? What forces do we have on our free body diagram?
There's gravity and friction.
Gravity or weight and friction. So gravity is always or weight is always downward. Friction, what is the direction of the friction? What is the motion of the box? Which direction is supposed to move? And how just tell me what direction should I put the friction on the box?
Oh, well, up to the right 30 degrees.
Exactly, right? Because the motion would be this box is going to slide down. Friction is always against the motion. So if that's the direction of the motion, friction should be opposite. So that would be my friction, Fk, moving the box. We want the box to move. So at the moment that it starts moving, that's the moment we're looking at this. Friction downward, upward, 30 degrees. And then we have our mg there. What else? Anything else? Yes, exactly. And going perpendicular to surface. There you go. So we are missing normal force there. It's always perpendicular to surface, applying to the object. And I'll just call this M. And that's pretty much it. There's nothing else. How about kinetic diagram? Which, remember, it's about to move. So it's not sliding on the bed, like the bed of this dump truck. Right? It's about to move. At that moment, it's not moving on the bed. But which direction is moving if it's part of the system? Which direction would be the acceleration of this box? Yes, so it should be to the right, right? Because if the box is not moving yet, it's part of the system, and system includes the box and the truck. So if the truck is going to the right with acceleration A, the box is also going to the right with the acceleration of A. So if that happens, meaning that the only component of acceleration on this is to the right. Now, the component of acceleration is A. Kinetic diagram, I have to multiply the mass of whatever this acceleration is applied to, or it belongs to. So that becomes ma, mass of this box with its acceleration. So again, box is sitting on a bed. The whole thing is moving to the right. Right? It's about to slide, but it's not sliding yet. Right? It's asking us find the acceleration, the smallest acceleration for which the box will begin to. If it was sliding already, you had some acceleration in this direction. But at this given moment, it's part of the system and not moving. And the system, including the truck, the whole thing is accelerating to the right. So your acceleration is A, and you have your mass. Right? Once you get this, the rest is just finding the components. Right? You just say summation of forces is equal to ma MA. From there, summation of forces. Let's take XY. You can do it in angle or just keep it as straight, because we have enough components in XY. You have to decompose Fn and Fj. If you turn it that way, you have to decompose Mg and Ma. So I don't know which one is more efficient. But that means this angle is 30 degrees, right? And as a result, this angle is also 30 degrees. These two are the same. So in x direction is equal to max. Motion is to the right, so I'm going to take right as positive. In y direction, there is really that much may. There is not that much of motion. Like you can just take either direction. I'll just take upward as positive, because there is no motion in that direction. It doesn't matter. So finding the components, looking at geometry, right? That's the part that we've dealt with a lot from hopefully statics. So summation of force in x direction, I have Fk, I have to decompose and find its component in x direction. So would be Fk cosine 30 degrees, right? Would be Fk cosine 30 degrees. To the right, so positive. Then I have n creates a component in x direction, which is negative minus n sine 30 degrees. Equal to, that's all I have in x direction. On my kinetic diagram, I have MA. So it becomes MA. My AX is A. Going to y direction. Looking at free body diagram to find the components on the left side. Upward, I have Fk sine 30 degrees. And I have plus n cosine 30 degrees. And I have my mg, minus mg. And there is no component of acceleration, kinetic diagram in y direction. This is there. That's pretty much it. The rest is just plugging in the values. Right? If I can even plug in here, Fk is equal to mu kn. And let's see, what can I do? Let's see from the first one. Let's call this 1 and call this 2. From the first one, I can find A. I just want to solve, basically, this is two equations, two unknowns, right? I don't know what NA is, and I don't know what N is. Don't know N, I don't know, well, that's pretty much it. The rest of the stuff, I don't know N there. So remember, this is also mu Kn. And I don't know N. So two equations, two unknowns. Mathematically, we can solve this. Looking at this, the first one gives you can find the acceleration from the first one, or maybe let's just start with the second one, because we can find n from the second one, right? So let's just start with the second one. N becomes, move things to the other side, becomes mg over mu k sine 30 plus cosine 30. I'm not wrong. Mu k sine 30 plus cosine 30. Yeah. Plugging in the numbers, you know everything here. You know m is, I can give you m. Very interesting. Should be somewhere. Give me a minute. Without m, we are just clueless here. I definitely didn't give it to you, and I cannot find it on the notes. Very good. Oh, now I remember. All right, that's interesting. I just remember what I did there. All right, so still dynamics is interesting. So we actually don't have M. That makes it more exciting. So we don't have M, right? I don't know what M is. Now, we actually have more unknowns. We don't know N, we don't know M, we don't know A. But let's see what happens if we just continue solving this. If I solve this by just plugging in the numbers, I know mu k is 0.64. Sine 30, cosine 30 are just numbers. So I can actually find this. This number will be 0.8432. And I wrote it as mg. This becomes n. Something mg. Now, if we go back and use the first equation, let's see what happens there. That's very interesting. If we use the first equation and I write it to find the acceleration, remember I'm finding the acceleration. This becomes, move things around, this becomes mu k n cosine 30 degrees minus n sine 30 degrees divided by m. Right? Now I'm going to factor out n from there. Right? So n becomes mu k cosine 30 degrees minus sine 30 degrees divided by m. Now see what happened. I found n as a function of mg, right? N is 0.8432. I don't know why did I go that far? Mg. So I can get rid of m here and m there. And the rest is what everything that I need to know is there, right? I know what mu k is, I know cosine 30, I know sine 30, I know 0.8432, g is just 9.81, so I get my acceleration. I like that problem. So if you do the multiplication and the math there, you'll get 0.0458 g, whatever that value is. Let me write it in a better form. We'll get A as 0.0, what did they say? Let's just round it up, 4g, 46g. That gives you your acceleration. Meter per second squared. If I can. Meter per second squared to be better with units. So let me remove this. It is still two equations, two unknowns, but there is a dependency there, and we use that dependency to find our unknowns. So here is my advice to you. You might ask, what do I do and how things work at the end? Sometimes you get more unknowns than equations, seems like. How do you know there is a relationship or there is some connection between some of those parameters? So here is what I suggest, as I said. Find the part that you have the most information about, or the part of the system that you're looking to find some unknown related to it. Either. Usually I suggest start with where you have the most information. If you don't have that, start with where you're asked to find the most find the specific unknown about. Isolate that, draw the free body diagram, put all the forces, draw the kinetic diagram, right? Make sure all the components of acceleration are there, apply multiplied by mass. Obviously, you need to know inertial forces. The right side is referred to inertial forces. because these forces are caused by the inertia, like mass or inertia. We'll talk about it later on when we get to rigid bodies. But write that, write the equations write the Newton's second law. Right? Summation of forces should be equal to ma. Right? Write it in x and y components when you're in Cartesian coordinates. We'll talk about our coordinate system later. But then look at your equations, plug in everything, and the rest is just math, playing around with your equations. So always the first few steps are exactly the same. Follow these steps, and then at some point you either get enough number of unknowns for your equation. Sometimes you don't, so you have to look at other part of the system and come up with an extra equation to help you to find your unknowns. Sometimes there is a relationship between the parameters you have there. You just have to move things around and plug in the values. You still get what you're asked to. In this problem, because of the way the system is set up, the mass of the box is irrelevant to the acceleration that you need to get to a point that the box slides. The box has to start sliding. See that box could be could have any weight. It could be 10 kilograms, 20 kilograms, 500 kilograms. It doesn't matter. The acceleration the truck had to reach, so the box starts sliding, wouldn't have changed. It was not a function of the mass of the box. All right. All right, I'm going to stop here. Question on this one, guys. All right. Let's get to the quiz. I have 2 minutes, so let's just let me